Hi everyone, welcome to Mostly Math. Today we'll be talking about a topic that's a bit more advanced than what we usually cover. We'll be talking about a topic from Einstein's theory of general relativity, which we'll abbreviate as GR for short most of the time. This is what I actually work on in between the videos as part of my own self-study, and it's actually pretty complex, and I just wanted to show you a topic that I'm covering today about how you would calculate the ordinary things that you calculate in this theory to show that they're not as strange and as difficult as they appear, just a bit tedious. So I am going to go through a few conventions. I'm not going to attempt to teach you everything that you need to know to fully understand this video. To do that, you'd have to have studied this theory at least a little bit by yourself, but I'll see what I can do. Okay, so throughout this video and in GR in general, we are going to be employing Einstein's summation convention. This is the convention that if we have if we have a series of indices, that they are to be summed over. So an example of this, if we have the metric for flat space, or just a metric at all. An ordinary metric is written as G mu nu dx mu dx nu, where we have mu and nu are variables that run from 0, 1, 2, 3, or we give these coordinates the names of time, x, y, and z as well. And for a flat metric, or flat space, we would have df squared is equal to minus dt squared plus dx squared plus dy squared plus dz squared. This is the kind of space-time that you've studied in other physics courses. Well, in Einstein's theory, we're going to have an arbitrary function of x, the g mu nu, that indicate how space-time changes. And this expression is really a shorthand for the following expression. We have a double sum equals 0 to 3 of the same thing. And if we had a diagonal metric, which is typically the case, if we had a g mu nu to be diagonal, so g11, g00, g22, g33, with all other coordinates being 0, then we could expand the sum as follows. It would just be gtt dx0 squared. I'm actually combining notations here. So it would be g00 dx0 squared plus g11 dx1 squared plus g22 gx2 squared plus g33 dx3 squared. And we would then assign these variables the name t, x, y, and z to conform to standard convention. Gtt dt squared plus gxx dx squared plus gyy dy squared plus gzz dz squared. And I'm going through this example to show you that the repeated indices are not meant to scare you. It's just a shorthand because we're tired of writing things that look like this. We just want to abbreviate it by this shorthand expression. And yeah, let's go get to the meat of our exercise here. It should be enough. I guess you need to know one more thing. So if we have a metric g mu nu to be a diagonal matrix, which is typically the case, which is exactly what I've written up there, gtt gxx, gyy, and gzz, then we're going to have this other symbol, g mu nu, with the indices raised as the inverse. So it would be the diagonal matrix of 1 over gtt, 1 over gxx, 1 over gyy, and 1 over gzz. This can be easily proven since this is just an index version of the following identity. If we have G inverse is equal to I, you can also write this as G mu lambda, G lambda nu is delta mu nu. They are the same thing. Just wanted to show you that we're going to be using the property that if we have something raised, it's just going to be 1 over it. Obviously, this is not intended to instruct you on this material. It's just going to be showing you what I'll be doing in the rest of the video, basically. Okay, that was just a brief introduction. It wasn't really meant to make that much sense. Just wanted to write down something like this so you've seen it before, so you won't be too shocked. It's still going to be pretty shocking for a first-time viewer, so definitely check out the Wikipedia page on Einstein's theory of general relativity for a more thorough introduction. All right. We are going to be considering the Kasner metric, which looks like this. We have ds squared is equal to minus dt squared plus t to the 2p, where p is some arbitrary real number, dx squared plus t to the 2q, another arbitrary number, dy squared, plus t to the 2r, dz squared. And what we want to show with this particular metric is that it satisfies the Einstein field equations. R mu nu is equal to 0, where this is the Reiki Tensor. Feel free to check out the Wikipedia page on this. It's equal to 0, and we're going to show this is true for a special value of p, q, and r. For 1 is equal to p plus q plus r, which is also equal to the sum of the squares. So what we're going to do is treat this as an ansatz, or a guess, and insert it into the simplified version of the Einstein field equation in flat space. And we're going to show that if we want it to be 0, we're going to set it to be equal to 0. Then this condition has to be satisfied. All right, let's get started. So the Reiki tensor here involves some very complicated objects, which I'm going to walk you through how to calculate. And it is going to be shocking if you're seeing this for the first time. But the purpose of this video is to show you that it's not shocking, it's just tedious, just a lot of derivatives and sums. Okay, so we need the definition of the Christoffel symbol. And this definition is as follows. Gamma of 3 Greek indices, rho mu nu, is 1/2 g rho lambda d mu g nu lambda plus d nu g mu lambda minus d lambda g mu nu. Now, according to our Einstein summation convention, there's only one index that's summed over. So this really should be written as a sum over lambda of the previous expression. But I'm not going to write it because I'm lazy. But notice we have the other indices, rho, mu, nu, are fixed values. And let's proceed in calculating some bad boys. Now, a typical exercise when you begin a problem like this is to think about which ones are going to be 0, since you know most of them are non-zero. So what you would do is you look at gamma t mu nu, for example, then write this out with mu and nu being free, and then show which ones are 0 for certain values of mu and nu, and then continue on to gamma x mu nu, gamma y mu nu, and gamma z mu nu. And they get easier as you go forward because along the way you find out that certain combinations are also going to be 0. I'm going to skip that argument. I'm just going to tell you which ones are non-zero, and if you're interested, you can go through this argument as well. Okay, let us begin with the first non-zero Christoffel symbol of gamma txx. all we have to do is plug t, x, and x into mu to rho, mu, and nu here, since we know that they all go from 0 to 3, or t, x, y, and z. And let's get started. Okay, gamma txx, first non-zero value is going to be 1/2 g t lambda, plug in x's on the bottom, x gx lambda plus d x dx lambda minus d lambda gxx. Okay. So, before we get started, I should note what we talked about before. So, we have g mu nu is equal to up here, diagonal of -1, t to the 2p, t to the 2q, t to the 2r. So, we have then g mu nu with the indices raised is the inverse of this matrix. Also a diagonal matrix with the entries 1 over t to the 2p. So 1 over t to the 2p is actually t to the minus 2p. That's how we're going to write it for the rest of this video. T to the minus 2p, t to the minus 2q, and t to the minus 2r. Unfortunately, I just don't have enough space to keep this up here. So you'll have to keep this in your head as we proceed. Okay, proceeding now. Okay, so off the bat we have a few being 0. In particular, we obviously have that the x derivatives are going to be 0 since nothing here in the coordinates depends on x. It all depends on t. So the only possibility left here is this term, which is this term here, and this inverse metric is only non-zero for lambda equals t. So it's going to be 1/2 gtt is a -1 here, lambda equals t, the time derivative of gxx, which is t to the 2p, which this is -1 of course, and -1 and +1 conspire to make 1. So we just get 1/2 the derivative of this, which we're going to compute as 2p, t to the 2p minus 1, which is just p to the t to the 2p minus 1. Excellent, done with that. Now I'm going to tell you that there are similar non-zero ones as well. Similarly, we have the other non-zero values of gamma t y equal to the same thing, but p replaced with q, q t to the 2q minus 1, and gamma of t zz as r, t to the 2r minus 1. So we have 3 non-zero Christoffel symbols already. Excellent. Let's go ahead and look at some more non-zero combinations. Okay, there's a second family here. Okay. Second family is like gamma of xtx. Let's start calculating. 1/2 gx lambda. So we have mu is equal to t and nu equals x. dt gx lambda plus mu is t, nu is x, dx gt lambda minus d lambda gtx. Okay, so let's see which ones are 0. Off the bat, we have an x derivative again, which is simply no good. Pretty sure. Yeah, x derivatives are definitely 0. Then we have a time derivative here, and let's see which lambda is going to help us out. We need lambda to be equal to x. So 1/2 gxx. And if lambda is equal to x, then this one goes away too, since x derivatives vanish. 1/2 gxx, time derivative of gxx. which is, okay, so we get 1/2 dxx, we get t to the minus 2p. Since if we raise the indices, we take 1 over the coefficient. And we have the time derivative of the same thing, t to the 2p, which we simplify as 1/2 t to the minus 2p. We got 2p here. I got t to the 2p minus 1, which is, these bad boys cancel. We get an extra factor of t. 2's cancel. So we just have p over t. Pretty straightforward. And similarly, we have the related family of gamma yty is equal to q over t. And we have gamma of ztz as r over t. So you see all these sums, all these Greek letters, they're really just a shorthand to avoid us writing things down because we're lazy. Let's go ahead, erase this, write down our results, and then start evaluating the Reiki Tensor, which is where the real work comes in. Gonna need the whole board for this bad boy. Okay. Notice GR is calculationally intensive, which is one reason why not many people go into it. It's just so darn hard and difficult to calculate anything. People would rather go into particle theory, where there's less tensors, though there still are some, and less indices to worry about. It's just easier, though it's more mathematically complicated since there's, variational fields of variational derivatives of quantum fields, which are much more difficult than just the classical mechanics that we're talking about.